So this week we're going to talk about planetary type circulation. Circulations are just wind in motion. Uh, when we have high pressure, we have a circulation, or we have low pressure, we have a circulation. So we're going to be dealing with that this week. We're going to look at it in a global scale, however. In other words, not in downtown Beckley or wherever. We're going to discuss it in, oh, this is what is happening over the whole globe kind of thing. So, what are the principal features that go into this, and how do they affect our weather? Well, we're going to look just quickly at the Sahel down in the southern part of the Saharan Desert. It's an area that can go from really dry to really wet. And understanding, and it's governed by a global circulation, a monsoon. So understanding that monsoon and how it can develop each year impacts how much agriculture these countries have. Some years it's so dry there's almost no agriculture. Other years, lots of it. And because of that, it's very hard for humans to live there. Yet there are a lot of people that live in that area. So understanding how this sets up each year is usually impactful for their lives. You can see where the land is there to the north of that large desert. To the south of it, very wet. So this is the transition zone. And that is key to the people that live there on how much food they're going to have for that year. So let's look at some of this at an idealized pattern. If the Earth didn't rotate, we'd have one side that was constantly dark and one side that's constantly lit. Near the equator would be the hottest spot where it's constantly lit because it would have the direct sunshine. We get, all kinds of air rising there, and it would all sink on the dark side. So you would just have one big circulation. Easy, right? Well, but the Earth rotates. So that immediately causes the Coriolis effect to begin to come into play, changes that circulation. And because it does, what we wind up with is low pressure over the equators, high pressure around 30 degrees north, and another area of low pressure that's up around 60 degrees north. These are general. If you were to look at a weather map, you would see these areas are generally where highs develop and lows develop. In between, transition zones. Continents, oceans, all of it impacts these big cells. So here you can look at it and say, oh yeah, there it is, 30 degrees north, nice high pressure. Big one over Siberia, another one here in this tropical Atlantic and across. Here's the low pressure down right along the equator. And then we do the same thing in the southern hemisphere. And you look at it up around 60 degrees, 50 to 60 degrees north, we got areas of low pressure. North of that, we have some high pressure. These will move with the seasons as well. And here you can see how westerlies along that low pressure dip down, bring cold fronts into our area in the wintertime, tend to stay further north in the summertime. The tropics may come a little further north in the summer, giving us more tropical weather, especially in places like Florida, along the Gulf Coast. So these subtropical anticyclones used to mess with the sailors when everybody used wind to have their boats moved. When Columbus came to the United States, for example, when they got into the center of these subtropical anticyclones, they couldn't move. So they always were trying to find the flanks of them where the wind would mow. So, and then north of that, we start getting into the westerlies where we live. Go south of that, you get close to the intertropical convergence zones. Way north is the polar vortex. It's circumpolar, it goes right around the poles, upper level, And it sits there with extremely cold temperatures in the wintertime, in our winter, and then obviously it develops in the southern hemisphere in their winter. And right along the edge of that is where some of the strongest temperature gradients develop. And with that, that's where we get the strongest jet streams. These jet streams are going to expand down into the United States during the wintertime, and they're going to tend to stay further north during the summertime. And notice with just everything we've looked at here is on a global scale. I'm not telling you that it's going to rain at your house tomorrow with this scale or that you're going to be bitterly cold. We're just looking at large scale pictures here. And here's the intertropical convergence zone. So the north of that, we have air moving. Literally, the easterlies are across to the north, and they're also across in the southern hemisphere. And what happens is they come together right here along the equator, and that causes upward motion, lots of thunderstorms, especially out over the ocean, and these will shift. Right now, we're in March. We're getting very close to the sun being directly over the equator. The intertropical convergence zone is very close to that area. Now, it will move north here with time into the summer. And these lines of thunderstorms and all will shift northward as well. If you live in the tropical islands, like Curacao or other areas like that, you'll watch this feature move across you. Much of the year you're going to be dry, but when this moves by, you're going to have significant rainfall, lots of storms. Okay, we're back into the mid latitudes here where the jet stream is, and you can see here it's a wavy pattern. It's not typically, oh, it just blows from west to east. Nah, it'll go in a wave from the northwest, come up from the southwest, and so on. With that, it messes up with the tropopause. We've been talking about that all throughout the course about how the tropopause is lower because the air is denser over the Arctic and higher where the air is less dense over the tropical sections. Well, in between where we live, these fronts will impact how the tropopause moves. And you can find it go higher or lower depending on how these fronts move through. All right, down the tropics, then there's another feature that really impacts tropics called the trade wind inversion. What it is, there's descending air, it's warmed by compression. Relative humidity decreases on the bottom side of the Hadley cell. That's just a little bit north of where the intertropical convergence zone is. So you get the upper level atmosphere gets dried out, gets warm. The bottom layer, however, may be a maritime layer. Think about Hawaii. Hawaii is in the tropics like this. On top of that layer is a trade wind inversion, so that the air aloft over Hawaii is very dry, warm. However, when you get down to the ground, Hawaii, right in the middle of a warm ocean, it has a maritime air mass, so the lower level can be pretty warm, humid, lots of showers around. However, because of that trade wind inversion, we don't get a lot of thunderstorms there. Gets lots of rain, but not a lot of thunderstorms. And you can see here how the intertropical convergence zone moves. Notice it moves some over the oceans, but boy, does it move a whole lot more over land. Land can heat up much easier than the oceans can. So because of that, it also cools off faster. The intertropical convergence zone follows the heat. All right. Even in a global circulation, some areas that are actually at the same latitude have very different climates. San Diego is exactly at the same latitude as Charleston, South Carolina. San Diego has almost no rain in the summer. Charleston, South Carolina has tremendous rain. There are high pressures out over the ocean. We saw them at 30 degrees north. They're centered over the ocean. San Diego is on the eastern edge of that high. The eastern edge tends to have northerly flow, so we're bringing cooler air, less convection potential. The air tends to sink. On the other side, Charleston has southerly air, more convective potential, and the air tends to rise. Notice which one gets lots of precip, the other one does not. All right, the ocean circulations. We've said that these general circulations persist over the globe. Well, because of that, they've actually set up circulations in the water. The Gulf Stream moves out of the Gulf of Mexico and up along the East Coast, all the way over into England, keeping it warmer than it actually should be. Part of that is circulation around the North Atlantic Gyre, that 30-degree north high pressure system. So you can see these circulations impact. Notice on the California, we have north. The big high here pulls the colder water down from the north along the California coast, keeping the temperatures colder. So there are these seasonal reversals of wind because of that occur. Two big ones. There's one in Southeast Asia and India. Summertime, that intertropical convergence zone moves north. If it moves north, what happens? The winds all of a sudden go from the south, pulling lots of moisture into India, gets lots of rain. The same happens over Southeast Asia, pulling lots of moisture up into the summertime. Now, in the wintertime, cold air coming out of Siberia, Mongolia, pressures south, you get no precipitation whatsoever, hardly. Very dry winters and cold. And you can see here there's how that impacts the rainfall. Notice here at New Delhi, tremendous rainfall, June, July, August, September. Then it just drops off into nothing. All because of the switching of the wind flow that boosts it. We have in the United States a monsoon. It occurs in the southwestern United States, New Mexico, Arizona, southeastern corner of California a little bit. Those areas, what happens is you wind up with very hot air initially develops there. The sun beats down, it's desert almost, like it gets very intense, the heat. You develop low pressure at the surface. Well, we know with low pressure, it means the pressure is going to drop slower in the atmosphere, so you develop high pressure aloft, and all that triggers a large circulation. Comes in off the Gulf of Mexico and even off of the Pacific, all kind of moisture into that area. And if you look at Tucson, Arizona, they get lots and lots of rainfall in July and August. You can literally watch the dew point will be sitting in the 40s out there, and all of a sudden it will move up into the 50s and 60s, and that triggers this huge rainfall event to begin. When you look at the waves in the upper atmosphere that move around the globe, we call them Rossby waves. They're long waves. They have little tiny waves inside of them, but these big waves, maybe 2 to 5 of them. And much of this winter, we had one centered over the eastern half of the United States. It didn't move, it just stayed there. When it did, it allowed littler waves to move down its slope into the eastern U.S., pulling Arctic air down with it, and it kept us cold, it kept us snowy, it produced a lot of precip in some areas, all because that Rossby wave didn't move. It's moving now, thank goodness. So here you can see, typically we have two types of flows in the atmosphere. One is a zonal flow, little waves, the west to east. The other, you get the much bigger waves. And when you get this meridional flow, you pull down a lot of cold air from up north, lots of warm air from the south, lots of moisture, and these can produce some of the biggest storms. The other week, we had a tremendous snowstorm along the eastern United States. What happened? You had a very meridional flow cold air plunged all the way down into the Gulf of Mexico. Warm air came up from the Gulf, all along the Gulf Coast there, and up into the eastern part, but all offshore. And right along that edge was where these big storms developed. We also get blocking patterns. We've had a lot of those here in the winter, and we tend to get a lot of them here in the springtime as well. What happens is if you get on the right side of them, you can have great weather. If you get on the wrong side of them, you can have bad weather. It lasts for days. And here you can see some of them that have prevailed in time. You get low pressure along the eastern United States, big centered high over the Midwest. This developed in the summer of '88 from almost record heat out here. Lots of cooler weather in New England. Here was another blocking pattern in '93. This produced some record rainfall, tremendous flooding along the Mississippi River, lots of severe weather. All right, jet streams form from the temperature contrast. We know that causes a pressure gradient. So the further up in the atmosphere you get, the more intense that pressure gradient becomes. That's what forms the jet stream. They form right along the frontal boundaries that are at the surface. And because of the balance between the Coriolis and the pressure gradient force, winds tend to blow parallel with these fronts. So here you can see all of that. And they can reach speeds over 200 miles per hour sometimes. You can see a seasonal shift. The polar front flips north in the summer, jet stream shifts north. Goes further south in the winter, jet stream comes south. There's also a tropical jet stream. Develops in the southern Pacific. Sometimes it merges with this jet stream and cause big storms. Also, there's a low-level jet that develops right across the Mississippi River up to the north. It surges at night. Interestingly, this causes a lot of nocturnal thunderstorms for parts of the southern United States, where it produces tornadoes with those thunderstorms. Short waves are just little waves that are rippling through these long Rossby waves. And when they do, they trigger a lot of convergence or divergence aloft. If they have divergence, what happens is the air is rising and you're producing low pressure at the surface, more convergence coming into the air there, creating bad weather. The opposite effect. And here's where the divergence and convergence are on that jet streak. If you're in the left front quadrant or the right rear, you get the divergence. Otherwise, you get the convergence. El Nino is pretty much the last thing we're going to try to get into. It's a global circulation, but it includes both the ocean and the atmosphere. And when you have warm El Ninos, you can see them here frequently along here, the southern oscillation. The red are the cold ones. And you can see that you get La Nina and El Nino. And because of those, you get water in motion. And because of that, the water tends to keep turning and moving to the right with depth. It'll pull away from the coastline. What happens is we get upwelling during the coastline. We also can get upwelling out in the intertropical convergence zones where the winds are coming together, pushing together at the top, causing upwelling at the bottom, which turns it away. So we wind up actually cooling under some of the intertropical convergence zone. And we get these on the east coast of the United States as well. Some of them can occur along the Outer Banks, where I have seen temperatures go from 80s one day to 50s the next, to back to the 80s again, all because of these upwelling events. You can see here how they impact conditions across the Pacific with this. Here, for example, is a neutral condition. Lots of thunderstorms in the western Pacific Ocean with that convective circulation develops, actually enhances the easterly wet jet there as well. In El Nino, on the other hand, air pressure falls over the eastern Pacific, rises over the western Pacific, which weakens the pressure gradient that we cause, and we wind up getting a very different pattern. Thunderstorms develop in different parts of the Pacific, and it impacts a lot of the United States as far as weather. La Nina has a lot of the opposite effects on the United States. Predicting these, we use satellite, different tools, global models. Currently, we're forecasting an El Nino developing this summer. We'll see if it happens. We look at a region in the Pacific on average temperature. Region Nino, region 3.4. If the temperatures are consistently at least 5 degrees below normal or 5 degrees above normal for at least 3 months, we consider ourselves into an either El Nino or La Nina. And here you can see all the various years that they've occurred. All right, there's other global circulations. We talk about the North Atlantic Oscillation. What that basically does is we measure the pressure difference between a high down over the Azores and a subtropical low, a polar low that's over Iceland. The greater the pressure difference, the stronger the NAO. These impact the eastern parts of the United States and lots of Europe. The positive ones tend to bring colder winters north of the polar jet stream, warmer winters just to the south of the stream, along the eastern United States. Negative ones, kind of more snowier winters. A lot of nor'easters may develop. You can see here the general look at that as well. There's an Arctic oscillation. We talked about a large circulation around the Arctics. Well, when this weakens, it allows that really, really cold Arctic air to move south into the United States or into Europe or even into Asia. So we look at the Arctic oscillation and say, oh, it's very intense, it's very strong, very positive. However, when it becomes negative, begins to weaken, it allows the Arctic air to move out of there. We wind up with lots more cold air coming in. And you can see here how they change literally by the month. There's a Pacific decadal oscillation as well as an Atlantic one we're going to talk about later, which can influence the west coast of the United States as well. Finally, there's a Madden-Julian oscillation. What it is areas of convection develop over the tropical Indian Ocean. They literally cause an up and down motion in the atmosphere that goes around the tropics or lower part of the westerlies all the way around the globe. These can influence tropical storms development. They can influence how much rainfall is going to come into the west coast of the United States. They can even influence if storms, extratropical low pressures are going to develop across the United States. They're very impactful, and we do track them consistently across the globe. So that's a lot I put at you here. So I think we'll just stop it right there.